All right, this is sort of part two. We solved this problem. We got V2 equals 3.5 feet per second with F equals MA. And it took about that much work. Now we're going to try and do the problem with work and energy. And first thing we do is we write the equation for work and energy. And so we know the initial kinetic energy, 1/2 mv1 squared, plus the work added to it, is for FDS. S1 to S2 is equal to the final kinetic energy. So there's a subset of these problems where the mass cancels out and like the masses in each term. And in those problems, you're not given a weight. And so that sometimes throws students. They get challenged because, hey, I don't know what the weight is, so how can I figure out the mass? But it turns out that the mass just cancels out. This one, it doesn't totally cancel out, but the reason I say that is I'm often gonna, try and get rid of the 1/2 m in front of both of those. And so I can do that. I can say, okay, if I multiply everything here times 2 over m, my equation will become, well, the 1/2 disappears because I'm multiplying it times 2. The m disappears because I'm dividing by m, and I'll have v1 squared plus, keep that 2 over m. Maybe I'll even put it in brackets. Integral of FDS equals, and the same thing, it disappears on the right-hand side, v2 squared. And we see what we're looking for a little bit easier there. What's the other video? If you're not sure where these come from, but I have, from this force, I have a component like that, which is 15 cosine 20. And from the weight, I have a component here, which is, it's either, let me do it this way, it's equal to W sine 20. And W sine 20 is equal to mg, right? W is equal to mg sine 20. So because of the 15, the mass isn't going to cancel out, but we see that we could cancel out the mass there. Doesn't really matter. But on some problems, you're going to want to write everything in terms of m and not in terms of w. The displacement is 1 foot along the ramp, and the only component of the force that matters is the amount of the force that is causing the displacement. So we very much need to, you can't say 15 pounds times 1 foot and say 15 foot-pounds of work. You can't say that because the 15 pounds is in that direction and the displacement is in that direction there. So this would be sad. We can't do that. But if we can, again, just visualize all the motion in that direction there along the ramp, we can say V1 squared is 2 feet per second. squared plus 2 over m. And since the forces are constant, we can just look at that as force times displacement. That's going to be, the force is the net force. It's going to be 15 cosine 20, right? That's in the direction of the displacement, s, and 15 cosine 20. But there's some force acting in the other direction, and I'm going to write it as mg sine 20. In this case here, we're going to, I'm going to cancel out the m's, but I got to account for it on this term. On some other problems, the m will cancel out everywhere, and you never needed to know how big the object was. It wouldn't matter if it was a 1 kilogram block or a 17 kilogram block. The result would be the same. So if you're not given weight, use mg and look for a way to cancel out the m's. Because if you don't know the weight, you don't know the mass. Don't forget, right? 2 over m is just my algebraic way of simplifying the equation. You don't have to do that. That's how I do some of them. 2 over m, that's why that exists. All I have is the force here. It's not uncommon that we accidentally forget to put in the s, right? The integral of ds is integral ds equals s2 minus s1. We say s1 equals 0 for this problem. S1 and s2 equals 1 foot for this problem. S2, and it's given us 1 foot. And checking my parentheses, everything looks good, equals v2 squared. And so I'm going to simplify this sum. I got 4 feet squared per second squared plus, in this case, the 1 foot is nice. It would have been 1.2 feet. We'd have to account for it, but the 1 will make it a nice, easy problem. And so remember, this is pounds, and this is weight, which is in pounds. So everything in these parentheses, this term is pounds, this term is pounds. And so I'm going to call this 30, 2 times 15, 30 cosine 20 over m minus, and now I'm going to cancel out the m's, and this is going to be 2, don't forget the 2, g sine 20. And now I've done all this math in one step. I multiplied that by feet, right? So this is pound feet, and this was pound feet, but divided by m. So this term is pound feet divided by the mass. Those are units. That's a dimension. And this one over here is pound feet, and I've divided by the mass. Or I will divide by the mass. But the feet are in there now. V2 squared. And if I substitute in, I'll do it the same way. 4 feet squared, I don't want to lose those, per second squared, 2 feet per second squared is 4 feet squared per second squared. This term becomes 30 cosine 20 pound feet divided by the mass, which is 30 over 32.2 slugs, right? Uncomfortable unit. Slugs, which is a pound second squared per foot. And if that throws you, make sure you check out the other video. I'll do it. No, I won't do it now. Right? And we see that when we flip that over, the feet are going to combine, and I'll have feet squared. The second squared will stay on the bottom, so I'll have feet squared per second squared, and the pounds will cancel out. I'll have the same units as that there. And this one is going to be minus 2, 32.2 feet. Remember, feet per second squared, but I multiplied it by feet, so G, which is in feet per second squared, times 1 foot is feet squared per second squared, and that's sine 20 V2 squared, and we get 4. All the terms are feet squared per second squared, just like we want, plus, and I want to, I want to bring it up. Didn't we do this math already? No, it's different numbers. So 30 divided by 32.2 is that 0.931. I know we had that before. That's our denominator here. So I'll bring it to the numerator by taking the inverse and multiply it times 30 times 20 cosine equals, I get 30.26 feet squared per second squared. And I'm going to subtract from that 2 times 32.2, 64.4 times 20 sine, and I get 22.03 V2 squared. And I'll make that negative. And I'll add to that 30.26, and I get 8.23. And so that's the number we had before. 4 plus 8.24 equals 12.24. 12.23, take the square root of it, we get V2 is equal to 3.5 feet per second. I want to talk about something else. In another video, I derived impulse and momentum, work and energy, substituting in the acceleration. Came out very nice. There's other derivations of that, and one of those derivations is with the dot product. This integral FDS is the same thing as F dot S, and I want to write that with you now. I want to look at this same problem with that. So I got the 2 squared and 2 over m, But everything after the 2 over m is the integral of FDS. It's the work done solved by multiplying f times s, but thinking about the directions very carefully. Let me redo that part with the dot product. First thing I'm going to do is write the net force on the object. The net force. There's 3 forces acting on the object. There's F in blue. There's the weight in red, and then there's the normal force from that other one. The normal force doesn't do any work because the motion is perpendicular to the direction of the normal force, so no work. Frictional force would do some, but there's no friction in this problem. It does no work. So if I write those other 2 as a vector, the net force due to the 30 pounds weight and the 15 pounds applied force is 15I, right? 15 pounds. And then it's minus 30J, that's the weight. Trying to get this here. I got another copy of this somewhere. Oh, I got another. There it is there. There's 3 forces acting on it. Normal force does no work, so I can neglect it. The net force, the forces that do work, the combination of them, you know, I wish this was like P. Then the net force is equal to P plus W equals 15I minus 30J, the weight. Just want to make sure you can see where that's coming from. 15I minus 30J. And then if I write S as a vector, right, it moves up the ramp 1 foot, but that's going to be 1 foot. Let me finish this one off with pounds. That's going to be 1 foot cosine 20 in the I. Look, 1 foot, 20 degrees, 1 cosine 20 in the I, plus 1 sine 20 in the J. Right, 1 foot, and so this has units of feet. So let's evaluate F dot S. Very easy, right? It's the sum of the I terms, 15 times 1 times cosine 20, right? It equals the scalar. Dot product is called the scalar product, 15 cosine 20, and then it's the sum of the next terms, which is minus 30 times 1 times sine 20. That's the work done to it. I want you to take a look over here. Before I put the 2 to make the 15 become 30 to solve it numerically, before I did that, it was 15 cosine 20 minus W sine 20 times 1 foot. This here has the units of multiplied this pounds times feet with the dot product. This is pound feet. Or the net was checking my camera, trying to show you everything, right? 30 times 20 sine equals, make that negative and add to it 15 times 20 cosine equals 3.83. Pound feet. So if I go back, I have two squared plus 2 over m, because I got rid of the 1/2 m on the 2. 2 over m, and everything in the parentheses up here comes down to 3.835 pound feet equals V2 squared. And again, I got 4 feet squared per second squared. And when I solve this, times 2 is 7.67. 7.670. Still pound feet, because the 2 didn't have any units. It was the 1/2 that I got rid of. It's just a constant. Divided by 30, the weight divided by gravity, pounds divided by feet per second squared, or this whole thing has units of pound second squared per foot. And when I do that math, the feet are going to go to the top, the pound second squared are going to go to the bottom. I'm going to have 2 feet at the top, feet squared. The pounds will cancel out. It'll be in feet per second squared, V2 squared. And so when I divide that number by 30, I'll have to change the lighting. Divided by 32.2, close parentheses equals, there's my 8.23. 4, not 2. There's my 12.23, which I got here, and I get V2 equals 3.5 feet per second. So the dot product can be very useful. Does the same thing. All right.